Hey guys, this is Math 148, section 14.2, partial derivatives. So derivatives are back. We're still looking at functions with two variables, which we were doing in section 14.1, but now we're taking the derivative in terms of one variable. And because we're only taking the derivative in terms of one variable, and there's two variables in the function, it's a partial derivative. It sounds very complicated, but it's somewhat straightforward if you are careful. So here's question number 9. Here's the function. C, in terms of xy, is equal to 600 minus 4x times y plus 10x squared times y. Okay, that's a function, sure. By the way, that function looks like this. How pretty is that? So it's this curving, saddly surface. And the question says, find, and this thing here, you read it dc dx, or the derivative of c in terms of x. I'm actually pointing at the screen like an idiot because you guys can't see what I'm pointing at. There, this one. dc dy, the derivative of c in terms of y. So again, you have this function. Imagine what is the rate of change in one direction, in the x direction, that's the derivative in terms of x, and then what is the rate of change in the y direction? That would be different, right? You'd be going like, woo, that way and that way, or whatever direction is x and y. So, in this case, we're taking partial derivatives. A couple of things to notice about partial derivatives. This notation, dc dx, that's the derivative in terms of x. Sometimes they write it c with a little x at the bottom. It's derivative in terms of x. Okay? And dc dy, sometimes you'll say c with a little y at the bottom. You'll see more of that in the next problems. So here we are. Question number 9. Come on baby, 9. We have c of x, y, x comma y is equal to 600 minus 4xy plus 10y squared. 10x squared y. Sorry, 10 times x squared y. So the first thing we're going to be doing is the derivative of this in terms of x. And I'm going to use a different color here to show you what this looks like. So in this case, we're saying that the function looks like this. 600 minus 4 times x times y. I'm going to make everything red except for the x's. See? So you can see the x's really well, okay? So now, do you see the yellow x's just pop out at you? So we're going to take the derivative of this function in terms of x. So we're just taking the derivative terms of x. So what do you do with the y pieces? You're going to treat y, or what's another word for treat? Act like y is a constant. So we just pretend like y is the number 2 or something. It's just some constant. It is a pi. So just don't treat it like a variable. So in this case, it's going to be equal to 600. Oops, sorry, the derivative. What have I done wrong? Do you see how I modeled something wrong to give you an example of what not to do? So the derivative of 600 is 0, because that is a constant, minus, what is the derivative of this piece? Well, it's 4x, but this is a constant, so the derivative of that is negative 4 times y. Why is that? Because negative 4x times y, the derivative of this piece, this is the only variable, and these two pieces are constants. So you could almost think of this as factoring that out like this. Sorry, that wasn't much factoring. Factoring it out like this for y times x. And now that piece is a constant. So minus 4y, and the derivative of this piece, well, plus 10, y is a constant, so it's just multiplied in front, and the derivative of this is 2x. Right? So your answer here is negative 4y plus 20x, because the 10 times the 2. So that's the derivative in terms of x. What is the derivative in terms of y? I shall rewrite it. So here's our function. Cx comma y is equal to 600, that was an equals to, very small equal signs, minus 4x times y plus 10x squared times y. But now we're going to take the derivative in terms of y. So think of it this way. That's 600 minus 4, x is a constant, y is the variable. What I might do for these, if you're taking the derivative in terms of y, is circle everything that's the variable. Because you're probably not going to want to get out colored pencils like this. So I did this in different colors so you could see the derivative that we're going to take the variable of, dc dy, the derivative in terms of y. So we're going to treat x like a constant. X is just some constant. We're just leaving it alone. Okay? Doesn't even matter. It's invisible to us. Treat x like a constant. My pen is acting a little strange. So in this case, the derivative of 600 is 0, minus this piece, the derivative is negative 4 times x, because we had negative 4x, that's a constant, times y. The derivative of that, remember, subtract 1, you get 4 to the 0. So, plus, this is all a constant now. That's just 10x squared. And what's the derivative of y? Well, that's just 1. So this whole thing equals negative 4x plus 10x squared. Ta-da! So the derivative in terms of y, I'm going to rewrite that. So dc dy, derivative in terms of y, is negative 4x plus 10x squared. Ta-da! So, again, going back to this problem, here's the problem. Here it is. Find dc dx and dc dy. So here's the derivative in terms of x minus, oops, look, I left something off of here, minus 4y plus 20x. This y should be down here. Y. So the answer here is negative 4y plus 20x. Y is the derivative in terms of x. Right? Do you see how awkward it is when somebody has messy handwriting? Okay. And then the derivative in terms of y is here. dc dy is negative 4x plus 10x squared. So I'm going to do another problem in another video.